So I think it's probably worth talking about question 16 and what it looks like, because you're going to be asked to finish this off at home. And Sam, I know you've done it now, but it might be worth redoing it because you did it on the whiteboard before anyway, okay? So let's just read through, and I'm not going to do the whole question, I'm just going to begin constructing it and talk through the strategy. So we've got a line, and it says that A and B are on L1 with some particular coordinates. So I'm going to draw L1, and it says I've got A and I've got B, and I know here lambda is 2, and I know here lambda is 5. So basically I can find out what those things are. It then says that point P has a position vector, and line L2 passes through the point P and is parallel to L1. So I've now got that there's another line that's parallel to it. I know how to write that line because I know about position vectors and direction vectors and how you make a line. But I'm not going to put P on it just yet, and you might see why in just a moment. So you'll easily be able to come up with part B. This is the bit I wanted to talk to you about. It says the points C and D both lie on the line L2 such that the distance between A and B, this distance, is the same as the distance between A and C, so probably somewhere over here is going to be C, and the same as the distance between A and D, so probably somewhere over here, like this. So we know that those three distances are equal to each other. Now, you know this coordinate and you know this coordinate. So the first thing that you're going to need to do for this last part here is you're going to find the distance, AB, and you'll do that by doing the magnitude of the vector AB, by doing B minus A, because by this point you know what the coordinates are of A and B. Then it just becomes, whatever that distance is there, it becomes the same problem as what you've been doing previously with knowing that these three distances are equal to each other. If you've used lambda for this equation, technically you should use mu to find out what these position vectors are as mu. And then P, we're hoping, is going to be in the middle. So my strategy to you would be to say, to show that P is the midpoint of CD, whatever this mu value is and whatever this mu value is, the quickest way to show that P is the midpoint is to show that this mu is the midpoint of these mu's, okay? So that's your strategy that you're going to do to be able to solve that question. It looks far more complicated, but it is exactly the same as this, A, It's exactly the same as the previous ones that we've done where you've got these distances. That one is A, that one is D, that one is C, and we're hoping that this point in the middle of them is going to be P. And we actually know what the value of this mu is for P because it's just the starting point, so the value of mu there is going to be 0. Okay? So we're going to leave lines for a bit, but we come back to lines. They're like sort of the building block of many of these problems that we have here. What we'll be doing with these things in the future is we will be modelling situations where, I don't know, like a pipe running underground is modelled as a vector line, or like a pipe running through a mountain is modelled as a vector line, and these might be different like positions of like workstations, and we want to say where should the workstations be positioned so that blah blah blah, you know, that's how they build these questions up in the future. So these vector lines will be coming up a few times, okay? So I just wanted to talk to you now about planes. We're going to extend our language of how we talk about vectors so that we're going to be talking about planes as well. We want to try and model as many real things as we can. And as soon as we go to 3 dimensions, planes become a very useful thing for us to talk about. And obviously by a plane, I'm not talking about an aeroplane, I'm talking about a flat surface. So it says here, we're going to look for the parametric vector form for the equation of a plane. And I'll explain a bit more about what this means in a second, what a parametric form is. So for a line, it says A is the position vector of a point on a plane. This time it's on a plane instead. And B and C are non-parallel vectors on the plane. How could we write the equation of the plane in vector form? So let's just simplify it and return to this idea of what it looks like to come up with the parametric equation of a line. When I say parametric, I mean we've got that parameter of like lambda in here. So with a line, I've said we could get a generic point R on a line by first getting to the line using A. So we could go onto the line by using A. And then we could add on some multiple of the direction vector to move somewhere else on the line. So we get the general position R is the position vector A plus some multiple of B. I want to try and think, could we do a similar thing with a plane? So this blue sort of parallelogram here is not really a blue parallelogram at all. It's a plane that we need to try and visualize in 3 dimensions. It's like the surface of the table that you're sat around. The origin is somewhere on the floor that we're talking about here. And the position vector A takes us up onto the plane. And then the position, not the position vector, but the vectors B and C are vectors which are parallel to the plane, but they're not parallel to each other. Any ideas of how we could use those 3 pieces of information to construct a general position on the plane? Like if you wanted to get to anywhere on this blue surface, how you could do that?
A plus lambda b.
Good. A plus lambda b plus mu c, because you can't use the same value of lambda. So what we're actually saying here is, first of all, you need to get onto the plane in the same way you just needed to get onto the line. If you just were able to add on some multiple of b, you would be fixed on this line that you've got here. But now you can move in the c direction as well as each other. So it's a bit like if you imagine like the table, and I don't know, this corner of this chair leg, table leg down here is the origin. First of all, to get up onto the table, there's a vector which takes it to this corner. That's going to be the a vector. Let's say that this is the b vector, and I don't know, any other one that's not parallel is the c vector. If I wanted to get over to where Shahan is sat, I would do the a vector to get over here. I don't know, maybe about 6 of these pens to run along here, or 5 of these pens, and then a few of these diagonal ones. Probably not going to go to Shahan with that many. Maybe just like 1 or 2 of these and a few of these pens sort of like added together. Because you can do any combination, as long as they're not parallel to each other, you can do some combination of them to get you to any point of the plane, because you can obviously go backwards as well by making the parameters negative too. So what you need to write down is this. Once on the plane using A, we could get to any other point on the plane using some amount of B and some amount of C. And those some amounts are the parameters. So what if you finish writing that down, what would happen if B and C were parallel? What would it be describing?
A line.
It would be describing a line, because you'd have R equals A plus lambda B plus mu C. But if B and C were parallel, it's the same direction. So you get onto the plane, and then your only option is to be able to travel along one particular direction, which means you're stuck on a line. So this is like a more general version of an equation of a line in a way. Like a line is actually a particular type of plane that is just got fixed in one direction. So must make sure that you use lambda and mu as separate ones, because you may not need to use a combination of both of them. The reason that we call this the parametric form is because lambda and mu are parameters. Lambda and mu are parameters. They're like the value that you can vary to try and get to wherever you want to get to for this. Now the parametric form of the plane is not a very useful form of the plane. It's useful for our understanding, and you need to know how to create this, but in the future we will be using a different version of the equation of the plane a lot more, and we'll try and learn how we can go from this equation to another equation in a little bit. Okay, so I'm just going to do a couple of these examples, and then we're going to do a different equation of a plane as well. Right, a plane. This time we use a capital letter of pi. just to describe the plane, because plane begins with P and pi begins with P. So we use line, we did like a lowercase l, plane, we do a capital pi. It's just what we do. So the plane pi, or P really, passes through these particular points. So these are the coordinates that are on this plane, and we're going to find the equation of the plane in that parametric form that we've got there. Now a little sketch may be helpful. So I know that there are these three coordinates. Obviously the plane isn't flat like this, it's going to be tilted in real life, but I'm drawing it flat. I've got A, I've got B, and I've got C. And in order to come up with the equation of the plane, I've got some origin that is down here. I need to get onto the plane to begin with, which is my position vector of A. And then I need two vectors which are on the plane. This is on the plane. I need two vectors which are on the plane that will help me to travel around it. Now I have selected the vector AB and AC. But what other vectors could I have selected? I could have done BC and BA, I could have done BC and CA, I could have done AC, I could have done any combination of two vectors that are on the plane. And for my position vector to begin with, I didn't need to pick A as the position on the plane. I could have picked C or I could have picked B. So there are a multitude of different answers you could do for this parametric form. And this is why the parametric form we don't like quite as much, because there's just so many things you could do. But it's a good way of getting into the question. If you can set up a parametric form, you can then make all of these other forms out of it that become a bit more useful. So let's work out AB. Well, AB is going to be B minus A, which is going to be 3, 2, minus 1, minus this, which is going to be minus 2, plus 1. So you get 1, 0, 0. Okay, so the vector AB is 1, 0, 0. The vector AC is C minus A, which is going to be 4, 3, 5, minus A, which is minus 2, plus 1. So 2, 1, 6. So putting this all together, we get that a general position on the plane is A, which is 2, 2, 1, 2, 2, minus 1. In fact, I'm going to do it a little bit slower, just so, because this is for our notes, let's make it look as useful as possible. The general position is going to be the position A plus some multiple of AB plus some multiple of AC, because AB and AC are the vectors which are parallel to the plane. And then putting that all together, we just get 2, 2, minus 1, plus lambda 1, 0, 0, plus mu 2, 1, 6. We don't usually write that in expanded or collected form. We usually leave that as the three separate things, just because we don't actually do many calculations with this. Okay, the line one, you can see why we put it together in the examples we were doing, because we did calculations with it. We don't really do calculations with this. But what you need to be able to look at when you see this, you need to be able to extract information. What information can you potentially extract from this? If I just gave you this, what would you tell me about it? You'd tell me the position vector of a point on the plane. You wouldn't tell me that that was A. You'd just say that's a point on the plane. And you'd tell me two vectors which are parallel to the plane. They're like the direction vectors, but you need two of them because it's 2 dimensions. Okay. So we're going to verify that P lies on the plane with this equation that we've got here. So I'm going to make this thing equal to this thing to show that it's on the plane. So I have 2, 2, minus 1. This is kind of the only chance we might ever write these things together. But we've got 3, 4, minus 2, plus 2 lambda, plus lambda, plus lambda, plus mu, minus mu, plus 2 mu. This is probably the only time we might ever write them together. And I can't think I've ever seen a question that looks like this. So what are we going to do here? What's going to happen? So simultaneous equations. So we're going to look at I and J, find out what lambda and mu are, and then hope it's true for this one as well. Yes, Ishak?
We do matrices.
We could do if you wanted to, but we're not going to. We're just going to do a quick simultaneous. So from the I part, we've got that 2 equals 3 plus 2 lambda plus mu. In other words, minus 1 equals 2 lambda plus mu. From the J part, 2 equals 4 plus lambda minus mu. So minus 2 equals lambda minus mu. Now you can either put those onto your equation solver in your calculator if you're feeling really lazy, or you've got this equation and this equation. Best way of solving those? There's a quicker way of doing that, don't you think?
Make lambda equal.
You could just add them.
Yeah.
But if you're just, you can use equation solvers on calculators at any time, unless they've said you have to show the algebra. So if I add these together, I would get minus 3 equals 3 lambda. So lambda is equal to minus 1. Now if I substitute in, I don't know, the top one, minus 1 equals minus 2 plus mu. So mu is equal to 1. So all I need to do now is check that the bottom one works, because if it doesn't work for all three, then it's not on the plane, is it? So I'll have a look at the k component, which says minus 1 equals minus 2 plus lambda plus 2 mu. So that's minus 2 minus 1 plus 2, which is equal to minus 1. So P lies on the plane. So there's a practice question we may do in just a second, but I'm actually going to go and push on to the other version of the plane as well, so I can set you some homework on it rather than spending any time next lesson doing it. Okay? So it's nothing super new, as long as we've understood how that plane is being constructed. There's an exam question here, but it's essentially the same as this one. They've just told you 3 positions on the plane, so you might get different answers to other people in the class here because, like I just said, there's a load of different ways you can come up with this. And similarly, these bits here, 1, 0, 0 and 2, 1, 6, what could you say you could have changed about these if you wanted to? You could have made them, it could have been minus 1, 0, 0, any multiple. You could have done 2 million, 1 million, 6 million, like whatever you wanted to do. Those ones can change. Can I change that one? No, you can't change that one because that has to be a position on the thing. Okay, so we're going to now look at a Cartesian form of the equation of a plane. We did the Cartesian form of the equation of a line, but we're going to have a look at an alternative way of doing this. And actually, we've already come across the Cartesian form of the equation of a plane. When did we come across it? When did we see images that look like this? Matrices. We already know the equation of a plane. What does the equation of a plane look like in matrices? Good. AX plus BY plus CZ equals D. That was the equation of a plane in 3 dimensions. So we already kind of know this, right? But I'm going to talk to you about where this kind of comes from. So an alternative approach to find the Cartesian equation of a straight line is to find a vector perpendicular to the line known as the normal vector n. So I've got this particular line here, and it's 0, 3 is its intersection point, and its vector of the direction is 1, 0.5, which means as you go across 1, you're going up 0.5. So in other words, the gradient is 0.5. So we can tell that the equation of this line is y equals 0.5x plus 3. But you can find the normal to the line as well, and this is just another way we could have done this. The normal vector is -1, 2, and you can sort of think carefully about why that works. If it's 1 across and 0.5 up, it would be 1 left and 2 up for them to be normal to each other, negative reciprocals and all of that coming together. So if this is the normal vector, then the equation actually turns out to be n1x plus n2y equals c, where c is a constant to be found. And I'm just going to show that by rearranging this one that I've got here. Or in fact, we've got it here. So we've seen that the normal vector is -1, 2. So we think it's going to be -1x plus 2y equals c. And because we know that 0, 3 is on the line, we've put 0 and 3 in place, which tells us that c is 6. So we obviously get 0 plus 6 equals c. So we get -x plus 2y equals 6. That's a different version of it. Now, if I just manipulate this a bit more, if I double everything, I get 2y equals x plus 6. And then if I subtract, I get -x plus 2y equals 6. So it just sounds a bit strange to say this, but if you know a vector which is perpendicular to the line, it will always be in this form here, where the x component of the perpendicular vector and the y component of the perpendicular vector, sorry, the I and j components, will go in front of the x and y coordinate, and it will be x and y variable, and it will be equal to some constant. So this is one reason that we might want the equation of a straight line to be in the form ax plus by equals c, because you can find out what the normal to the line is. It reminds us a bit of the standard form that we use for the equation of a straight line, which I think I must have done about 3 or 4 months ago with my Year 12 class. That's sometimes why we like to have it written in this version, because it helps us to find out a normal direction to it as well. Don't worry if you don't fully grasp all of this. I will be able to teach you, once we've learned something called the scalar dot product, why this works. But for now, you just kind of have to trust me. It works in 2 dimensions, and it's going to work in 3 dimensions. I'll then prove it to you later why it works after we've learned a new technique. So if this is how it is for a line, that you just do a normal here and here, it's going to be the same thing for a plane. You can extend the idea. So this plane that I've got here, a normal vector to it is a vector which is perpendicular to the plane. So right now, it's like my bottle sat on the table. The direction of the bottle is perpendicular to the plane. And there's actually only really one unique direction that this bottle can go in that is perpendicular to it. It can't obviously go at an angle like this or like this. It could be going upwards or it could be going down. It is unique. The direction is unique. Obviously, you can have multiples of that direction. So the equation of this plane that we've got here is you take the I, j, and k component of the normal vector, and you place it in front of the x, the y, and the z, and it's just equal to some constant c, just like it was with the 2 dimensions. So for the questions you're going to get in this exercise, they will tell you what the normal vector is, and they tell you a particular point that it passes through, and we'll try and find out the Cartesian equation of it. So for the normal that we've got here, we think we're going to have that the equation of the plane will be 3x minus 2y plus z, because of the 3 minus 2, 1. And we think that that is going to be equal to some constant, c.
Why is it k?
Why is it what, sorry?
K. No, 3 I, j, k. Okay, it's I, j, and k.
I, j, and k.
I'll get mixed up with z.
Sorry, yes. And now we're going to say that this point is on the line. So in other words, the point with position 8i, 4j, minus 7k has this coordinate, which is x, y, z. So if I substitute these in, I get 3 times 8 minus 2 times 4 plus minus 7 is equal to c. So it's 24 minus 8 minus 7, which is 9. So the equation of the plane pi is 3x minus 2y plus z equals 9. Now, if I were you, I wouldn't feel very convinced about what I've told you here. I've just told you this is the equation of the plane. So next lesson, when I see you on Friday, we will be learning some maths that will convince you that this is the equation of the plane. And it's all to do with this normal here. It's quite strange because all of our definitions of like lines in the past and planes today have all been to do about directions of the plane or directions of the line, things that are parallel to the line or parallel to the plane. And now randomly I've said to you, oh, hang on, if we knew something better, if we knew the normal or something perpendicular, we can come up with something new. It probably does feel a bit odd that I've just said this. The reason it's useful is because if I was going to say, oh, tell me a vector which is parallel to this plane, the one that Shahan would think of would be different to the one that Haroon was thinking of, which is different to the one that Arifal was thinking of. But if I said, tell me a vector that is perpendicular to this plane, then you'd all be thinking of basically the same one. They may be different multiples of each other, or one might be positive or one might be negative, but they would all be the same direction. It is unique. So this is why we're aiming for it to be in this kind of unique way. It just allows us to do a lot more interesting things with it. And it's no longer going to be this form that I said wasn't so great, because there's loads of different ways of doing it. This is pretty unique. I mean, obviously you could multiply everything by 10 or 100, but that's the only way you could write that equation of the plane. So your homework is going to be just to use some quite simple ideas of those ones from exercise 9B. I'll write the questions out for you to do on Padlet, but it's basically going to be these ones that we've got here, as well as these ones that we've got here, and they are largely just using the techniques that are from these examples and this example that we've got here. For now, trust me on this, and next lesson we'll do some quite interesting things with vectors that hopefully will convince you a bit more.